Can you hear me? Okay. So, good afternoon everyone. I'm Jacopo Massa, and today, also thanks to my supervisors and colleagues, Professor Stefano Forti and Antonio Brogi, we are all from the University of Pisa in Italy. I'm going to present the work that started as my master thesis, and now here we are talking about data-aware service placement in the Cloud-IoT continuum. So, first of all, I want to talk to you about the context. Most of you, of course, already know that we are implicitly declaring a layered architecture, a layered infrastructure, where the cloud is the upper layer, populated by these hundreds of data centers that has, of course, huge processing and storage capabilities. On the other hand, we have the IoT layer, where billions and billions, according to recent surveys, billions and billions of IoT devices populates this layer with, if we compare to the Cloud One, of course, very low processing and storage capabilities. Here we have namely sensors and actuators that are devices that respectively produce and consume data. And of course, if we consider those applications that are latency sensitive or bandwidth hungry, we can't, for example, send everything to the cloud to respect these requirements. So we introduce this middle layer that we can call in several ways: fog, edge, mist, osmotic nodes, according to the paradigm that we are considering. But in general, we introduce these nodes because we want to filter partially the data that we produce to respect those latency and bandwidth requirements that application must have and devices that are in the IoT layer. Also, in this context, we must consider multi-component applications. So those applications that are built in a service-oriented way, they are made by several processing components that namely we call services, and that exchange information and data within several interactions. Now, knowing the context, we can go on the problem that we considered and we tried to solve. So, first of all, we know how the application is made by services and end-to-end interaction between them. On the other hand, we have the infrastructure made of nodes with divided into layers with several levels of capabilities, as we have seen before. And we wonder where to place each application service on an infrastructure node. And once we have decided how to place each service, how to route the traffic between the placed services in a quality of service and context-aware manner. Now, in the current state of the art, as it is stated in this, but also at tons of other surveys, the application requirements and dually the node capabilities, so what a node has to provide to host some services, all this stuff is in terms of, first of all, software, hardware, and IoT. So, for example, how much space, if we need some specialized hardware or some particular devices needed by a service to work and to be executed. Then we move on the latency and the bandwidth. That are the two metrics we have considered to describe our quality of service, our QoS. These two metrics were also used in our modeling to describe and define the end-to-end interaction between the services, but also the links between the nodes of the infrastructures that we used. Another crucial and fundamental aspect is the security. In these surveys that we have analyzed, security is mentioned, but only in a few words, and it is never related to the data. And this is a step forward with respect to the state of the art that we have introduced with this work. And last but not least, as I told you before, once we have decided to place each service on its node, we want to route the traffic between this service, considering, of course, all the other requirements that we have already mentioned. So, knowing the current state of the art, knowing the problem, we set some goals. First of all, we wanted to add the data awareness to the problem that we are considering. So, we devised a declarative modeling, and we will see why declarative, a declarative modeling of both Cloud-IoT infrastructures and multi-service applications in a context, quality of service, but also data-aware manner. What does it mean and how we do that? We considered all the data that appear that are used by the considered application. So, for each data type, we have called the data type, we consider some of their characteristics. Of course, the size, in this case the punctual size of the datum, then the transmission rate, and pay attention to the fact that these two metrics can change for the same datum if it appears in different interactions between different and several payload services. And of course, as we are in an IoT context, we consider also sources and targets that, again, we namely call sensors and actuators. As we will see next, all of these characteristics are fundamental during both the placement and the route findings. By the way, after having declared this, after having devised this declarative modeling, we exploited a continuous reasoning approach to speed up the decision making and adapt the solution at runtime. So once we have found a first eligible placement and routing, we observe and monitor both the infrastructure and the application and try to change the solution at runtime with the new observed state. Last but not least, we have, of course, implemented and assessed everything in a Prolog open source prototype. Why we have chosen Prolog? For many reasons. First of all, for its simple syntax that allowed us to be very compact and to make fast prototyping, in the sense that the whole code base is 120 lines of code, and so it is very simple to manage and update. Not only for this, but especially because Prolog uses a backtracking technique to explore, to find a solution, if any, of course, but it ensures an exhaustive search of the solution space. So, as I told you a while ago, we exploited this continuous reasoning approach because we wanted to adapt the solution that we have found at runtime. This is a technique that is used a lot, especially in large-scale problems like the one that we are considering. So, how we did that? We can say parallel reasoner. Each time that we find that the infrastructure of the application has changed. For instance, a node or a link falls down, or a new service is added to the application, two services are merged, and so on and so forth. Of course, since we want to obtain a speed up, we can't redeploy everything. We must find a solution to obtain the speed up. How? We focus only on what we have called suffering services. So we reduced the size of the problem and we paid the attention only to the services that cannot meet more the requirements due to the new observed state. And by doing so, we obtained significant results that I will show you in a while. But before going on the results, I want to show you figuratively how our tool works. And I will show you also some code snippets to let you understand how powerful it could be to write something like that in Prolog. So, let's consider this application made by three services that are communicating as described by the arrows, and each service has some IoT requirements that, of course, it requires to be executed. We want to place this application on this very simple infrastructure made by 5 nodes. Each node has its own different capabilities and has also some, this time, physical devices attached to it. Now, if we run our tool that, as spoiled in the previous slide, we have called with a lot of imagination DA Placer, which stands for Data Aware Placer, we obtain a mapping of each service to one node of the infrastructure. And as can be seen by these colored arrows, we have also an indication of which will be an eligible route that each communicating pair of components has to use. Communicating entities could be a pair of services, a sensor and a service, or a service and an actuator, of course. Now, let's imagine that after a certain time, a certain period, the node AP2 falls down, and with it all the links that he had. For the sake of simplicity of this presentation, imagine that the device named Axel 20 is moved by the infrastructure provider. But anyway, if we rerun our tool, now, since we have already a solution both for the placement and the routing, we will only move for this instance of the problem, the interface service, and recompute all the routes that involved that service, without moving the rest of the application on the rest of the infrastructure, and only checking that all is continues to be okay. Now, as promised, I want to show you briefly two code snippets. Both for let you know how powerful is the problem, but also to see where the data awareness lies. So this code snippet show you the checking of a node that can or cannot host a service. So first of all, with the first two lines, we check that the service and the node are in the so-called knowledge base of the reasoner, and then we perform the checks. So, for instance, the software, the hardware, and the security. For the security, here there is a first look on the data awareness, because security requirements are obtained by all the data that the service uses in all its interactions. But, as I told you before, a node, to be eligible, must also have eligible routes that starts from it and involves the service S. With this other code snippet, I want to show you that also during the route finding, the data awareness is important, because data are used to understand which is the maximum required, the maximum latency and the minimum required total bandwidth needed in an entire data flow. And data flow means a route in the infrastructure. Because as you can see from the third line, for each end-to-end interaction, we have a list of data that appears in that interaction. This list is a list of pairs where we have the datum and the transmission rate, one of the characteristics that we have seen before. This information within the size that is in the description of the datum of the data type is used by the predicate getPW that takes in input the list of all the data that are used in the interaction and retrieves the maximum bandwidth in this case, using both size and data rate. Okay, so as promised, now I can show you some of the average simulated results, and I want to underline simulated because we tried the tool on real-world applications, but not on real test beds in the sense of infrastructures. We have simulated and generated randomly the infrastructures. So, experiments are in terms of execution times and inferences made by the prolog reasoner, and we compared the exhaustive approach, where I mean the tool that finds the first eligible solution, and secondly, we compared with the continuous reasoning approach. So, these first two graphs show the results for the exhaustive search. So, we Oh, I forgot a detail, that we used also 4 different variation rates, which means that we used a certain, with a certain percentage, we randomly changed the infrastructure to simulate its changing over time. It is worth noticing that increasing both the infrastructure size but also the infrastructure variation rate, both the metrics increase. But more interesting is to see what happens with the continuous reasoning. On the same scale of the previous graphs, we can see that both of the metrics have maximum values that are more or less an order of magnitude less with respect to the others. And we obtain, in both cases, a positive speed up that, of course, on average is 21 times for the execution and 13 times for the inferences. Now, it's true that speedups are always positive, but to be honest and transparent with you, speedups are positive, but they decrease also here, increasing the variation rate because, of course, we are moving the sub-problem, the partial problem, to the original one, which means that we are moving to this general complexity that could be big O of n to the s, where n is the number of nodes, s is the number of services that we want to place. Secondly, speedups decrease, increasing the infrastructure size, and this time is the default is because we have to find routes on larger infrastructures, and also here, very generically, the complexity is dictated by the average node degree, which is that we have named k, and d, that is the diameter of the network, that of course increasing the size of the infrastructure. Okay, just to conclude, I want to recap what we have seen and what were the steps forward with respect to the state of the art, starting from the addition of the data awareness to the placement and routing problem, because mainly we focused on the joint placement of the joint problem of placing both data and services. I mean that in the literature this joint problem is not so addressed because they focus only on one of these 2 aspects. Then we have introduced, or better, we have strictly related security requirements to the data. And last but not least, we have used this continuous reasoning approach to adapt at runtime and to adapt the found solution at runtime, if any, and speed up the whole process. This work is, of course, at its infancy and has several limitations that will bring to several future works. First of all, we want to extend the model also to serverless and fast paradigm. My other colleagues have could explain better than me which are the requirements needed in this other field, but you can imagine that are more than the one that I've shown you. Then, as you have seen, we do not have a metric to evaluate the goodness of a solution. We retrieve, if any, the first eligible solution, both for the placement and the routing. So we could optimize some metric, for example, the cost of the placement, the sustainability with several metrics, or the packing of the application to reduce the number of nodes that we want to, on which we want to place the application. Then, so far, we have managed only migration decisions of services, and we could add other decisions like the scalability according to the workload of services, or merging, remove, undeploy some services, or in the perspective of osmotic computing, we could place several versions of the same service with a different level of capabilities to create, we can say, adaptive applications. Then, again, we have validated our solution only on simulated infrastructure, so one of the future works will be for sure to try the model on real test beds. And finally, I received a lot of comments by other colleagues that to build the product knowledge base is not so user-friendly. So to create some tools that can help the user experience will be for sure one of the other future works. And with this I have ended. Thank you for your attention.
So you spoke about the quality of service.
Oh, sorry.
So are you so when you do, are you trying to optimize the quality of service, or are you looking at the different metrics?
Okay, not optimizing, because as I mentioned, we do not have an optimization of nothing. We only ensure that there is a placement that respects the quality of service that the application infrastructure provider decides. Okay, so in our knowledge base, the infrastructure provider will say that between this node and that node there will be this latency and this featured bandwidth. Can the application be placed with this situation? We can say no or yes in this way.
Right.
Okay.
Any other questions?
Thank you for the nice talk. Did you also take into account things like, if you want to have something really reliable, you from the very beginning you start with having duplicate nodes doing the same work, substitutes automatically, deploying things on different nodes. If you, for example, know that you're the same functionality on different nodes, then you know the nodes are unreliable on the edge or whatever. Did you take these things into account in your placement algorithms?
You mean automatically change at runtime?
No, it's the very beginning having things like redundant nodes, and then one node crashes and nobody matter. It doesn't matter because it is a redundant automatic.
Statically, no. So not since from the beginning. Also because we can talk better to the poster session of this more in detail, but the reasoner, of course, as exploits prolog and backtracking and so on and so forth, is non-deterministic. So it finds the first fact that respects those requirements that you tell to it. So the short answer is no, for this reason.
That was my impression that prolog may have a problem with this kind of...
Yes, because you could do that, but you have, for example, to sort the facts in your knowledge base, and you pay for sorting. So you have to find the right trade-off between what you want and what you need.
Thank you very much.